Okay, folks, welcome to the next lecture. And in this lecture, we'll be taking a look at an introduction to calculus. So, first of all, what is calculus? It's a very large field in mathematics. There's essentially three different parts to it. The study of limits allows us to examine function behavior as our input values get really, really large or really, really small, or else when we're trying to look at a particular point of interest, which often mathematically we can't look at directly, like an asymptote, what's happening when we get very close to an asymptote. So limits in itself is quite a complex field of study. We've introduced them briefly with the idea of Zeno's paradox, and when we were looking at exponential functions, but we won't examine limits really in any detail in this module. Another field of calculus is the study of integrals. This allows us to study how a function accumulates area. So if we can use integrals to find the area under a curve, and this is lots of different applications in science. But again, integrals and integration we need to study the third area first, derivatives, before we study integrals. So again, integrals and integration won't really be a part of this module. The area we're most interested in is the study of derivatives, and this is kind of the foundation stone of calculus. Once we understand derivatives, then we can start to study integrals in more detail. And in maths, integration and differentiation. These two are often regarded as the inverse of each other. So there is strong links and correlations between the two, but the study of derivatives nearly always comes first. So that's what we'll be looking at. And derivatives studies the rate of change of a function. And more importantly, it actually gives us the instantaneous rate of change. And that's what we're going to examine in this lecture in particularly. How do we find this instantaneous rate of change? So that's the topic, differentiation, rate of change. So we're often interested as scientists in this instantaneous rate of change. So for example, microbiologists to be interested in the rate of growth of a microbial population as time passes. A medical scientist is interested in how quickly a drug is being absorbed by the circulatory system. Wastewater scientist needs to know how flow rate is related to pipe diameter. And nutritionalists are often interested in the rate at which a food type has been absorbed by the digestive system. So anytime we come across these words, rate or how quickly, as soon as you see the word rate of change, you can be fairly sure that derivatives are going to lie at the heart of our analysis. So finding the instantaneous rate of change between 2 points is fairly straightforward. So we'd usually have a line, we'd find 2 points on them, we'd find the change in y over the change in x. And that's fairly solid maths. We'd know then m is equal to y2 minus y1 over x2 minus x1. However, finding the instantaneous rate of change, so if we're only interested in 1 point, that's a completely different manner. And this is what we're looking for all the time. I want to know, if necessary, to 10 decimal places what the slope is at any point on a curve. This is quite tricky. So what we're trying to do is find the slope of a curve at a point P. So here's the curve, and we're particularly interested in what's the exact slope at that point P. Mathematically, what we're trying to do is find the slope of the tangent t at point P. So this is what we're trying to find. We want to find the slope of that tangent. And we're going to take a look at kind of a fairly simple example, first of all, a ball being thrown, and then we're going to transfer that kind of knowledge back into a more general mathematical framework. But first we've just take a look at slopes in a more formal manner. This is just what I was saying in a couple of slides ago. The slope is dy delta y over delta x. Delta y, change in y, delta x, change in x. And we're more familiar with the slope formula. This one down here, y2 minus y1. Remember, it's always vertical change over horizontal change. So with a straight line, it's fairly straightforward because the slope never changes. If we have 2 points, we can always find the slope, and we know then that the slope is going to be the same regardless of where we look on that line. If, however, we're taking a look at a curve, so we look at a simple example like a ball being thrown, which is usually given by a quadratic function. Here's our quadratic function, and we've looked at this example earlier when we looked at quadratic functions several weeks ago. Sketch a curve of the function. Determine the height of the ball at 5 seconds. Determine the speed and direction of the ball after 0.5 seconds. Determine the height of the ball at 0.5 seconds. And then determine the maximum height reached by the ball. So this was an example we looked at earlier. And what we had to do was we sketched the curve first of all. Then if we were looking for the height at 5 seconds, we would read back off our curve. So everything would depend on the accuracy of our curve. If we were looking for the speed and direction at the same time, we'd have to draw a tangent at the point of interest. And remember, when we were drawing tangents, we were discussing about how well every student would draw that tangent at slightly different angles. So everyone would produce slightly different values for. Well, the speed is the change in height. So for each student, determining the slope of that tangent is going to produce slightly different results. We'd need to pick a second point on the tangent and then use our slope formula. y2 minus y1 over x2 minus x1. If we feed in those values, we can determine the slope. But how do we know this is accurate? This is our big question, and as scientists we need accuracy. So this was the big problem with drawing graphs and drawing tangents to curves, is there was always human error involved, and we need to eliminate that human error. And that's what derivatives allows us to do. If we needed to determine the maximum height reached by the ball, again, it'll be a little bit of a guessing game. We'd have to draw a horizontal line from where we consider to be the peak of the curve and read then back off our height axis as to what was the height at that particular time. So these are all kind of issues with drawing graphs and trying to arrive at accurate answers from these graphs. So drawing tangents is not ideal for several reasons. Time consuming, not particularly accurate. If we needed to determine tangents at several different points, the graphs would get very cluttered. So there must be a better way. And there is, thankfully, calculus, and in particular, in this particular study where we're looking for slopes of tangents, differentiation is the skill set within calculus that we use. And as I said, this is one of the most important branches of maths for scientists and engineers. So now we're going to take a look at just the underlying theory behind differentiation. And differentiation has loads of different names. It can be called differentiation, finding derivative, finding the slope of the tangent to a curve, the rate of change, the rate simply. So there's loads of different words to describe the same process. So I'll use them interchangeably, but don't be put off. They all mean the same thing. Everything we're doing in this lecture is all about finding the slope of a curve at any point we choose. So we're going to go back to the ball being thrown, but we're going to kind of do it in a much more analytical way. So we've met the thrown ball example and the issues that arise with trying to use graphs, hand-drawn graphs, to analyze our any answers we may have. And we're asked to find the height and speed of the ball at 0.5 seconds. So imagine we have a powerful motion triggered camera positioned right beside the ball at this time of interest at 0.5 seconds. So we're going to take a picture of the ball at this time and measure its position at this exact time. So at 0.5 seconds, we measured the ball is at 1.4125 meters height. And if we were to create it as a point on the curve, it'd look like this, as I've written down here. Now this value, 1.4125, we could find that by using the function. So if we use the height function and let t equal to 0.5, we would get that answer. But we're using the camera at the moment to determine everything. Very accurate camera and very, very sensitive. So what we're trying to do now is we want to find the slope of the tangent at this point of interest, but the problem is we only have 1 point. We need 2 points to find the slope. At the moment we've only got 1 point, and this is our problem. And this is what is in this slide here. We want to get the speed of the ball, and in order to get the speed is a rate of change, it is a slope. But as we've seen up till now, in order to get the slope, we need 2 points. At the moment, we've only got 1. We've only got this point. But to find the slope, we need 2 points. So we've only got half of what we need. So what we're going to do is pick a point that's very close, pick a time that's very close to 0.5 seconds. And then find the slope between this new point and the point we're really interested in, which is this one. And then we can kind of be reasonably close to the answer. So we'll take a look at 1/100th of a second later. So we need to select a point which is really, really close to this point of interest. This is our point of interest. And then what we're going to do is, with this new point, we're going to make it move closer and closer to this point here. And essentially the idea is we move this kind of imaginary point so close to this point that eventually the distance between the 2 points becomes negligible. And when we've achieved that, then we can say we can find the slope between our point of interest, this imaginary point, which is infinitesimally close to it. And once we know it's infinitesimally close, we can assume then that the slope between these two values will be very close to the instantaneous speed. And we'll use limits to explore when the gap between the 2 points becomes infinitesimally small. So that's what we're saying here, that delta x, the gap between the 2 points, becomes very, very small. So again, guys, just to kind of re-emphasize, we have only 1 point of interest, this one. But in order to find the slope, we need another point. That new point is going to be extremely close to our point of interest. And the closer we make those 2 points, in other words, the smaller the gap between them, the closer and closer we're going to be to the instantaneous speed. That's the whole premise that derivatives are built on, or differentiation is built on. So now remember our ball. We had our ball at one position at 0.5 seconds. This was its position. And now we're going to take a look at, well, 1/100th of a second later, where is the ball? So 1/100th of a second later, 0.51 seconds. Our camera registers the position of the ball as here. And again, we could find this position by feeding this value into here. But our camera is doing the work for us. Now we've got two positions. We can work out the change in height, what's the difference in height, over what's the difference in time, delta H over delta T. So we get the slope between these, so it's y2 minus y1 on the top, x2 minus x1 on the bottom. And that's what we have here. When we do the maths, we get this, and when we work it out, the slope of the line is 0.9445 meters per second. Remember, on the top we're measuring meters, on the bottom we're measuring seconds. And this, meters per second, is speed. So now we've got the average speed between these 2 points. But as scientists, we're kind of going, that's not 1/100th of a second, is still, it's a tangible difference. So we're going to make the gap between them smaller. On the next slide, we're going to take a look at, well, what happens in 1,000th of a second. So there's our initial position, and now we just move 1,000th of a second beyond this point of interest. And this is the position of the ball. We have a new point. And again, we can get the slope. What's the average speed of the ball between these 2 points? Delta H over delta T. We have the maths here. And when we work it out, we get a new speed, which is a little bit closer than the previous slide, or a good bit closer. It's 10 times closer. But again, you might go, not 1,000th of a second. Again, it's a tangible difference between our point of interest and this new imaginary point. So if we go down to 1,000,000th of a second, here's the initial point, our point of interest, and now we move 1,000,000th of a second beyond that. And the ball is here. So the ball, obviously in 1,000,000th of a second, the ball will have moved only a tiny, tiny distance from where it was at this point. This is the new point of interest. The figures are getting a little bit unwieldy now. But again, we get the slope between these 2 points. And we get this value. So now we're getting very, very close to the speed of the ball at our point of interest. On the next slide, I actually go on and bring it into 1,000,000th of a second, but just the numbers got too unwieldy, so I'll just give us a quick review of what we've done so far. In 1/100th of a second, this was the average speed between the ball in its original position and the new position 1/100th of a second away. At 1,000th of a second, this was the average speed. At 1,000,000th of a second, this was our average speed. And like I said, we could go on to do it with 1,000,000th of a second. And this is the average speed between the ball at the position we're interested in, and then 1,000,000th of a second away from it. The slope between those two gives us this. So I think you can kind of see that as we make the gap in time smaller and smaller, our speed is heading towards a limiting value. So as delta t gets really small, the speed of the ball gets closer and closer to 0.95 meters per second. And this idea is called the limit in maths. So this is also where limits comes into with calculus, but we're just going to kind of accept it. I think you can agree that as the gap gets smaller and smaller, the speed of the ball tends towards this value. And this, guys, is the basis of differentiation. We want to make the gap between our point of interest and a new point infinitesimally small, that they're so close together we can say they're almost the same point. But there has to be a tiny gap between them, otherwise our slope formula doesn't work. So this maths, when we make the gap incredibly small, we use this terminology here, the limit as delta t goes to 0 of delta h over delta t. This is just the slope formula. And essentially that little bit at the start gives us our instantaneous, and the bit on the right gives us the change in height over change in time, which is the slope. So this formula gives us the instantaneous slope. More commonly, it's just written as dh dt in terms of the example we were looking at, because remember our function was, our output was height and our input was time. Sorry, if you remember the original function. So now in more general terms, using x and y instead of h and t. So this is more of a mathematical definition, and it's a more kind of formal, rather than looking at ball and height and time, we're just using a point in general and x and y. So in terms of x and y, there's our instantaneous bit and there's our slope. And again, our output is y, our input is x, so the instantaneous slope is more usually called dy dx. So whenever you see dy dx, guys, don't let it put you off. It simply means the slope of the curve, but it's the instantaneous slope, which is very, very powerful. And that's just what I'm saying there. Dy dx simply means the slope, but in particular the instantaneous slope. So now in a more mathematical sense, it's the exact same idea. We're interested in finding the exact slope at this point P. Mathematically, we're looking for the slope of the tangent at the point P. But remember, with a tangent only touches the point at the point of interest. So we've only, again, we're back to the scenario, we're only interested in this point P. What's the exact slope at that point P? But the same logic applies. In order to find a slope, we need 2 points. So here's our point of interest. We choose a new point, which is extremely close to P. Now I've expanded things out to try and make it visually more acceptable, but this again, the idea is here is that we're a billionth of a second, or whatever x is in this case, away from P. This on a graph, the distance between these two would be barely visible. If we were to draw a line between these points, we could find the slope of that line. Now note, this isn't a tangent. This line would technically be called a chord because it's cutting the curve. But it's really just a line. And the slope of that line is delta y over delta x, as we know. Now on the next slide, we're going to make the gap smaller. So delta x is going to become smaller, just like we did with the ball. So now delta x is smaller, and again the slope of the line that joins these, the average slope of the line, is delta y over delta x. So the idea is the same again, guys. We're making delta x smaller and smaller in each slide. On the next slide, I make the gap smaller again. And again, a line that's not a tangent yet, but we're getting closer and closer to L becoming a tangent. And that's what we want. We want to keep going until the gap between x and x plus delta x is so small that we can say it's negligible, and then we can say the slope of L is equal to the slope of the tangent, which is what we're interested in. So again, L is delta y over delta x. And now in this last slide, I've moved the point. It's negligibly close to P. It's incredibly close to P. So if you notice there it is appearing. It's essentially on the same point. And now when we try and draw a line between the 2 points, we're very close, or we're practically at the slope of the tangent t. So notice the line's name has changed from L for line to T for tangent. So the slope of the tangent is the slope of the line as long as delta x is incredibly small. Just putting a bit of formal maths on it, the slope of t. Remember, delta y over delta x was the slope of L. And then, in more formal language, all of this is called dy dx, the instantaneous slope at the point P. So that's what dy dx is, guys. I know it confuses students an awful lot, but it's really just that slope, but the instantaneous slope. So it's important to realize that delta x approaches 0, but it can never actually become 0, because then we're back to having 1 point, and we can't find a slope from simply 1 point. We don't have enough information to use our slope formula. Now, the next bit is I just put a bit more formal, kind of a more formal rendition of this. Here's our point of interest, the new point. And now if we kind of write these, so that this is x down here, and this point down here is going to be x plus delta x. So first of all, we identified a point xy. But instead of calling it y, remember we can use the more kind of general notation and say, well, the position y depends on x. It's a function in x. Similarly, when we look at our new point, x plus delta x, when we write that as an output, rather than calling it y plus delta y, we can say, well, the output is a function of my input. So on the y-axis, we're just using the more general notation for functions, which we met back right at the start of the module. And now the slope between these is delta y, the change in y over the change in x. And that's what our function becomes. On the top we have this minus this. So again, it's just really y2 minus y1. And on the bottom, it's x2 minus x1, but the x's will cancel out. And this now is kind of more formal notation for the derivative function, but don't worry about it too much because we won't be using it. I used to use it years ago in class, but we don't really look at it so much anymore. And now we're going to bring in the idea of the limit. So we're going to make that gap between the 2 points infinitesimally small. So as delta x approaches 0, this function starts to look, and particularly the delta y over delta x. So remember, this is for slope, and this is just another way of describing the slope, but using the function notation. And that's all written then, dy dx can be described using this function. Now, This is the basis for what's called differentiation from first principles. And you might have met this in secondary school. It's quite a clunky process. And I have a video describing the process on Moodle. You can take a look at it if you want. And it shows you how dy dx is arrived at using this function. Now, we don't do it in this module because it's quite tedious and students generally tend to hate it. So we're actually going to shortcut this process. And we're going to look at differentiation by rule, where essentially somebody much smarter than me has gone through the differentiation from first principles and produced a set of rules, which allows us to arrive at our answer much, much quicker. These rules are available in all kind of log tables, all formula tables and stuff like that. So in the next lecture, that's what we're going to take a look at, differentiation by rule. There is examples of differentiation from first principles in the video section if you want to take a look at it, but like I said, it won't be examined as part of this module. So that, guys, is the kind of basis of differentiation. We're looking to find the instantaneous slope at any point on a curve. And that's what this notation means. So we'll finish up there, guys. Thanks very much for listening. I know it's kind of conceptually, students can often struggle with it, but I hope that video makes some sense. So thanks again, and we shall chat to you for the next video.